Hello everyone. Welcome to a short series of videos on the topic of integration. Now, as many of you know, integration is a topic in calculus which goes hand in hand with differentiation. And earlier in the course, you've already learned a fair bit about differentiation. By the end of this section, I hope that you'll have a clear understanding of how differentiation and integration are two sides of the same coin. So let's start with some motivation. Let's start with a simple question. What is integration? Well, I want you to have two concepts in your mind as we go through. Firstly, integration is a method and a toolkit for finding the solution to questions like, what is the area under a curve? So if I have some function, little f, that defines a curve, and that curve makes an area with the x-axis. So that area here goes from x equals little a up to x equals b, and I can write it like this. A equals the integral of f of x dx. And here the integral is taken from x equals a to x equals b. So, what are the parts of this integral called? Well, we have f of x, that's called the integrand in this context. Dx is the measure of integration, a is the lower limit, b is the upper limit, and this is the integral sign. Okay, well so far that's just notation. We've written a concept in terms of symbols. Later we'll see how to actually evaluate this in specific examples. But for the next part of the course, I want you to think about integration purely as the inverse of differentiation. In other words, integration is the opposite process to differentiation. In other words, again, if I can take the derivative of a function, I can take the integral of a function. If the derivative of capital F is little f, then the integral of little f is capital F. And I can write that like this. The integral of little f with respect to x equals capital F. And hopefully you can see that there's an inverse relationship here. One more subtlety, I have to add a constant of integration because this is not uniquely defined. Now, I'll talk about this in the next clip. Let's start with a definition of indefinite integration. Here's the definition. A function capital F such that the derivative of capital F equals little f is called an indefinite integral of little f. So in other words, to find the indefinite integral of little f, we need to find some function capital F whose derivative gives little f. That sounds complicated, but it's not. There's a way to write the indefinite integral. As you can guess, it involves the integral sign. We write the integral of fx dx equals capital F, not forgetting to add a constant of integration, that's c. Well, why is it that we add this constant of integration? It's because I've written here an indefinite integral, the indefinite article. So this is telling us that actually the indefinite integral is not uniquely defined, because we can always add a constant here. Why is that? It's because the derivative of a constant is 0. So now if I take the derivative of this new function f plus c, and using the fact that I can differentiate separately, I can write that like so. df by dx plus dc by dx, and we know that this is 0. So in fact this function also satisfies our definition because this is just little f. So in other words, the indefinite integral is not uniquely defined, it's defined only up to a constant of integration. So don't forget to include this. Integration is a linear process, just like differentiation. So that means we have some very simple operations which we can write down straight away and would probably use without even thinking about them. Firstly, addition and subtraction. If we add together two integrands and then we integrate the whole thing, that's the same as separately integrating the integrands and then adding them together. So let me write that like this. the integral of f plus g is the same as the integral of f plus the integral of g. So we can split the integral like so. And the same thing would apply if we had a minus sign here. And the other simple relationship is that we can, if the integrand is some function multiplied by a constant, then we can simply pull that constant out of the front of the integral. So I'd write that like this. In other words, the integral of alpha f is the same as alpha times the integral of f when alpha is a constant. Now, let's see how we can put this idea to good use. The key idea is that integration is the inverse of differentiation. What does that mean in practice? It means for you that each function that you know how to differentiate will lead you to a function you'll now know how to integrate. Let me show how that works in practice with a very simple example. A simple example would be that capital F equals x raised to some power n. Okay. Now the first thing to do is to take the derivative of this function. Well, that's simple to do. I can write the derivative as f prime as a shorthand, and I just have to take the derivative here. So what happens? I bring down the power and I lower the power by 1. Hopefully very familiar for you. Now, I've got a function I can differentiate, which means that I have a function I can integrate. And so I can write this side like this. I can say that the integral of n x to the n minus 1 dx equals x to the n plus the constant. There we have a result. It's a useful result, it's valid. However, it would be even better if we could rearrange things so that on this side we had something that looked more like x to the n. So let me do that by saying let n equal m plus 1, where here m is a new constant, which is just 1 less than n. Then I can bring this n out the front here and write that as m plus 1. Then I have the integral of x to the n minus 1, which is the same as m. And on this side, I have x to the n, which is the same as x to the n plus 1 plus c. Well, it's good. I brought this constant out the front, and finally I can divide through by n plus 1 to reach a final result. And here it is. The integral of x to the m dx equals 1 over m plus 1 x to the m plus 1 plus c. And all we've done here is we've used the fact that integration is the inverse of differentiation. So we see that whereas differentiation lowers the power by 1, integration raises the power by 1. And in both cases, there's a constant which corresponds to the index, which you have to take care of. In this case, it's 1 over m plus 1. One final remark. This is generally valid for any value of m except for m equal to minus 1. You can see that if m were equal to minus 1, there would be a problem here because we'd have 1 divided by 0. And going back to the original case, m equals minus 1 is the same as n equals 0, and that would correspond to a constant here. So this is a special case, and we'll do this one next. If you were watching that last clip closely, you may have seen what looked like a mistake on my part. When I went from this line to this line by dividing through by m plus 1, I divided this term by m plus 1, but I didn't seem to divide the c by m plus 1. And to be technically correct, of course I should. But the thing is, c is a constant which at this point we don't know its value. Also, c divided by m plus 1 is another constant. So I could say, let's call this c tilde. But I could even say, let's call the original c tilde, and let's call this c now. And so that's the line of logic which allowed me to just write c, apparently making a logical mistake. But you'll see that repeated in many derivations, so it's something to watch out for.